P-charts are useful for monitoring attributes. Attributes are essentially yes or no questions. Strangely enough, the manager here who's concerned about the proportion of red candies in a mix is asking yes or no questions about the candy or the product. Is it or is it not red? Now let's take a look. A manager wants to monitor the proportion of red candies present in a 5-color candy mix. For 8 hours, the manager has gathered exactly 50 candies every hour. This is important. We want to note that to the side. We have just been told the sample size. Lowercase n is the size of the sample. Okay. By randomly selecting and emptying one 50 candy bag produced by the candy mix packaging machine. Oh, okay. During the 8-hour shift, the manager was assured the candy color mix was under appropriate control. Examining the 8 samples gathered reveals the following amounts of red candy. So, you take a bag that has exactly 50 candies in it, that is essentially a sample out of this huge wave of output that's coming out of the packaging system. Empty it out. You're looking at each candy. Yes or no. Is it red? Collecting the data. Now, first question. What is the mean and standard deviation of natural variation in the sampling process for the proportion of red candy? Oh, okay. Now, we have 8 samples. These 8 samples, this is exactly how many red candies were in each sample. The manager is concerned about proportion, so you know what? The first thing that we need to do here is to take the actual count number of candies and just change it into proportion, which isn't too hard because, for instance, in the case of the first bag or first sample that was pulled, there were 10 red candies, of which it's been stressed there's always 50 in a bag. So 10 divided by 50 reveals that for that first sample, the proportion, which is denoted lowercase p, is 0.2 or 20%. That first bag was 20% red candies. Oh, okay. Now what we need to do is we just need to do this logic for all of the samples. Okay, so for the second sample, there were 12 red candies and there's 50 in a bag. So 12 divided by 50, I get 0.24, 24% red. For the third sample, 11 divided by 50, 0.22. For the fourth sample, we're back to 10. 10 divided by 50 is 0.2, exactly 20%. For the next sample, 8 divided by 50 is 0.16, 16% red candies. Then 13 divided by 50, 0.26. And then 11 divided by 50, we're back to 0.22. And then 9 divided by 50 equals 0.18. Now, what's the question we're trying to ask? First off, what is the mean of this natural? We say natural variation because we know the process is in control. That is also known as P bar, right? P is for proportion, bars for average. What the question's asking is what's the average proportions that we observed? Oh, okay, so what I would want to do is take this data that I've just generated here, these numbers right here, and average them. Average them together to obtain P bar. I get 0.21. If you were to average the numbers that we revealed through our arithmetic, then the average is 0.21. On average, there's about 21% red candy in each one of those bags, okay, or P bar. Now, that's only half of that question because it asked for 2 things. It also asked for the standard deviation in what we're observing. Oh, and we have to remember there's a particular formula for that. For the standard deviation in the proportion, sigma for standard deviation, lowercase p for proportion, that is the square root of P bar. Oh, that's good that we calculated this first. We're going to need it, times 1 minus P bar divided by n. Oh, all right, so fill in that particular formula. Now that we have P bar, we're looking for the square root of, oh, right, 0.21, right, that, times 1 minus 0.21 divided by, and be careful, 50. Right, it said that there were 50 candies in a sample. Why did I say be careful? Remember, n is always the sample size. N is always the sample size. N is never the number of samples. Sometimes people get distracted by that, like there's 8 samples here. You never do anything with that information. All right, anyway, so I put the numbers in, but what's the result? On my calculator, I get, okay, 0.0576. 0.0576. Yes. That is the standard deviation in the proportion of the sampling process when it's in control. Oh, okay, now we have, it asked for 2 things, and now we have them both. There's the mean, and there is the standard deviation. Okay, what else do they want to know? If the manager uses z equals 3.0 to create a p-chart, right, why were we doing that? In part A. To continue monitoring the proportion of red candies in a 5-color mix, what will be the upper and the lower control limits? We just need to remember how you calculate upper and lower control limits for a p-chart. On a p-chart, the upper control limit is p bar plus z, right? That's why we were supplied 1, times the standard deviation in the proportion. Oh, okay, lower control limit is p bar minus z times that same standard deviation in the proportion. Oh, okay, no wonder we found this and found that in part A. This is supplied right here. We only need to fill this in. Because from part A, we know that p bar is 0.21 plus, they just specified a z of 3, times, that's the 0.0576. For the lower control limit, 0.21 minus 3 times 0.0576. So I get upper control limit of 0.3828, lower control limit of 0.0372. Oh, all right, so what this is implying is they should draw a chart of which you would chart future proportions of red candies in a bag of 50. You would tolerate everything up to about 38% of the candies turning out to be red, and everything down to about it's a little bit close to 4% of them being red. Anything in between you're assuming is natural variation. Anything outside of that, too small or too large, that's what you're declaring as suspicious or assignable variation. Oh, all right. There's your limits for a p-chart. Now, last question. Suppose the manager is mistaken in the belief that each bag contains 50 candies. In reality, the number of candies in each bag can vary quite a bit, so the manager is resolved to use a C chart instead. Assuming the same level of confidence as in part B, okay, which means that Z of 3, what is the upper and lower control limits of this chart, and how does this chart compare with the C chart, or the P chart from part B? Oh, all right, the P chart, the proportion chart from part B, was relying on that n equals 50, that the samples were always of size exactly 50 candies. What this last question is saying is that, no, really, that's not true. Maybe sometimes they're 49, sometimes there's 53. At that point, there's no nice, neat n equals 50. Oh, so instead of a P chart, a C chart. C, lowercase c, as in count. C charts refer to the number of occurrences. Oh, now, first off, we need the formula for the C chart because it's asking what the limits would be. So let me note first just the formula. In the C chart, your upper control limit will be C bar plus Z times the square root of C bar. The lower control limit will be C bar minus Z times the square root of C bar. Oh, but wait, in order to fill this out and answer the question, we need C bar. What's C bar? And it's pretty simple. Go back to the original data. In the original data, remember we made this column here, it was P, the proportion, right? C charts are even simpler. This is C. over here. C, as in count. C is referring to the number of occurrences. These are the actual number of occurrences of interest. You know, we were interested in some reason in red candy, so this is C. So C bar is just the average of that column. So I get that C bar, if you average these numbers here, the actual observations, is 10.5. On average, across those 8 samples, 10.5 candies were red. That's the number that we need for the C chart. Oh, okay. So 10.5, 10.5. Because to draw the C chart, you first do the computations, 10.5, right, C bar plus 3. Why 3? Because the question said the same confidence interval as here. That's what Z is establishing, which means use the same Z times the square root of 10.5. There's your upper control limit. Lower control limit, 10.5, minus 3 times the square root of 10.5. So I get upper control limit of, you know, just put this in the calculator, 20.2 technically. That's what the calculator is saying. Lower control limit, 0.8. That's the actual limits of the C chart. And I said technically as in, right, you can report these numbers. I mean, technically that's where you would draw the lines. That's what the calculator is showing. The reality is in the future, if the chart were used, what would they be charting? They'd be charting the number of red candies they saw in the sample. And then, you know, not really sure what the sample size would be, but it'd be the number of occurrences. The number of occurrences would always be a whole number. I mean, because there can't be, well, technically there shouldn't be like 10.5 actual red candies in a certain sample. Oh, which means that basically if you saw up to 20 candies, that would be inside the limit. If you saw 21 candies, that would be outside the limit. If you saw as few as 1 candy, that's still in the limit, but you don't become alarmed until you see no candies, 0, because that's outside of the limit. Anyway, those are the limits of the C chart. Now to finish out this question, they snuck in another query. It says, how does this compare to the P chart in part B? Oh, well, we can see here the 2 sets of limits from part B to part C. This is an actual count of red candies. This is a proportion of red candies. So at first it looks like, well, how am I supposed to say anything intelligent about comparing these two, because aren't they like apples and oranges? Yes and no. This is a proportion, that's an actual count. But if you wanted to comment on the generosity or the pickiness of one chart versus the other, there is a way to compare. And that is, oh, by the way, go back to the P chart. The P chart is assuming that there's going to be 50 candies in each sample. So if you have 50 candies in the sample and your upper control limit is 0.3828, exactly how many red candies is that? What count would that basically convert to? Oh, okay. Well, I could, just a little bit of scratch work. This is the actual control limits for the chart. I don't want to confuse that, but I'm doing a little bit of additional analysis. And I'm saying, oh yeah, so if you had 50 candies in each sample, okay, 50 times 0.3828, I get 19.14 versus 50 candies times the lower limit of 0.374, I get 1.87. Now I can make a commentary. Basically, right, now remember actual number of red candies would be a whole number. Basically, the P chart is saying if you see up to 19 red candies, that'd be okay. It'd be in the limit. If you saw 20, it'd be outside the limit. If you see as few as 2 blue candies, that would be okay. But if you saw 1 blue candy, that would be outside the limit. Interesting. These are similar. See the 20 and the 1 here? These are similar limits. The limits are similar. Limits of C versus P chart similar. Actually, I can comment here, P chart is slightly narrower. Because the C chart would tolerate 20 candies. 20 candies would fall inside the limit. And just right there at 20 candies, that wouldn't work with the P chart. That would fall just outside the limit. But 19 candies would work in both charts, right? 2 candies would work in both charts. 1 candy would fall outside of the limit of the P chart, but not the C chart. Okay, so we see that they actually are related to each other. They create a similar interval based on confidence, although the P chart is essentially slightly narrower.